To talk about derivatives, we are not to shortcuts yet, but you are close, and that was really weird. Not sure what just happened there. There we go. Helps if you hit the right one. All right. But sometimes, in some types of functions, do not have derivatives everywhere. So we talked about that the derivative is that general equation that will tell you the slope at any given particular point. But sometimes, because remember, to find the derivative, you take the limit as delta x goes to 0, correct? So that fishing analogy is you cast that lure out there and you start reeling it back in. What we look for are some weird changes in the behavior of that. So here are some instances where a derivative actually won't exist, because it is a limit, correct, as delta x goes to 0. So let's say I wanted to find, and just watch for a second. If I wanted to find the slope right there, I could cast the lure that way and it would reel back in, correct? And I could cast it out that way and reel it back in. Would both of those values be the same? If I was coming from the right and from the left, would they be reeling back into the same value? They would, so that limit would exist, correct? And it would be whatever that value is, possibly a negative something, correct? That slope would be, right? But do you see any points on this particular graph where I might have trouble doing that? Where I might have trouble of it coming to the same value? And again, we're talking about slope here. Not just the y value, but slope. Any points that might be a problem on that graph? If I go out that way, again, we're talking slope. If I cast that out, do you agree this slope right there is a positive slope? It continues to be a positive slope as I reel it back in. How about if I go out that way and I reel it back in? That's a negative slope. So the limit coming from the right is positive, the limit coming from the left is negative. So does that limit exist? It can't possibly, because they're not even, can't possibly be coming to the same value. Okay. So when you have stuff like this, it's sometimes called a corner or sometimes called a cusp. Okay. Those are things that you're going to want to watch out for in your functions or in your graphs. Okay, because you cannot take the derivative there because it's going to different values. Okay. Another one that's a problem are these right here, and that's because you end up with, the point that's a problem is here, because you bring it out this way, it's going pretty good, but this is kind of the tangent that you end up with, correct? You with me on that? And what's the slope of that? Undefined is the slope of a vertical tangent, correct? A vertical line, the slope is undefined. Do you think that's a slight problem for a slope going to that value? Yeah, because can you see it, even if I reel it in from this way, are they both approaching that same line though? Are they both approaching, can you see the lines in there like that? Kind of working its way towards that? And back in this way? They're working their way towards that vertical tangent, which unfortunately has an undefined slope. That's a problem. Okay? Because the limit is approaching something that doesn't even exist. Okay? And as you can see, here is a third type of problem. Does anybody remember what function that might be? From past things? Yes? No, quite. The answer was 1 over square root of x. No, not quite. That's an interesting graph, though, in itself. Yes? Absolute value of x? Nope, that's number 1, is the absolute value of x. This is actually the greatest integer function, which you don't talk about a lot. It's a step function. Okay, it just keeps jumping. Do you see how there might be a problem with this one? Might be some problem points for finding a derivative. Okay. No problems at all. None. Okay. Yeah, I mean, but what if I'm trying to reel in there, reel in there? They're not even connected. You have a slight problem there? Yeah. Any other ones you can think of that might cause a problem? True, but the points are in 2 different locations. You see what I mean? Yeah. There's a huge gap. All right? Yeah. So can you think of another type of discontinuity that would cause a problem, potentially? Nope, that's not the one. The one that's down below in your notes is not the one I was talking about. Any other functions we've dealt with that might have a problem with finding a derivative at all values? Any functions? 1 over x, give us some problems. What kind of problems do we get with 1 over x? Asymptotes. Very good. Okay, so other problems we could have is asymptotes. Okay, because as we look at 1 over x, is there a spot that's a problem? Could I find the slope, say, right there? Yeah, the derivative is valid there. Could I find the slope right there? Yes. Where's the one spot I can't find? The slope is where the asymptote is, right? Okay. But then that isn't part of the domain, so keep that straight. The book, as I said, adds this one. I kind of think it is very similar to the other one. It looks a lot like a cusp to me, or you could even see it is, in this particular case, it is kind of working its way towards that vertical tangent again, correct? It's kind of both in this case. It's that sudden change in direction is always going to give you problems. Okay? I think that's what it says here. The book actually calls this one a flat out a cusp. Or you could call it a spike. Okay? A lot of those words are kind of thrown together, either spike, cusp, a corner. They're used very interchangeably. Okay, this is huge. You might want to star this, highlight it, whatever it is you want to do. Continuity versus differentiability. If you remember, continuity means as you take the limit of that function, it's equal to the y value. This is talking about slope, though, is what differentiability is talking about. So it says if f of x, some function, that's all this means, if some function is differentiable, what that means is I can take the derivative at some x value. Then, if I can take the derivative there, I can guarantee you that it will be continuous at that same point. Without a doubt, it has to be. But remember, continuous means as the limit approaches that value, it's the same as the y value. That's what that means. That's what continuous means. Differentiable means that the limit of those slopes is approaching the same value. They do mean different things. Now, here's where a lot of people get messed up. They believe that if f of x is continuous at that value, then I have to be able to take the derivative. No, you might be able to take the derivative, but we don't know for sure. Because didn't I just give you a bunch of them that are actually continuous, but you can't take the derivative somewhere? Right? Just talking like y values now. As I bring it back in, am I approaching that point from the right? As I bring it back in, am I approaching that point from the left? Is the point actually defined there? So that is continuous, right? But what did we just say about that point? I can't take the derivative there, or the derivative's not helpful there, correct? So just because it's continuous does not make it differentiable. If I can take the derivative there, I can guarantee you it's continuous there. Yes? X equaling C? X equaling C just meant that they chose some value. Yep, they just chose some value, and notice how they kept it the same. Yep. They're saying at that same X value. They just picked one. The reason they choose that is normally we say, oh, from A to B, oh, there's some C in the middle. Right? That's normally that's why they chose C. That really is huge. If it does not make sense, you need to come in and talk to me, because it really does need to make sense to you. Okay? So if it didn't, hopefully this will clear it up. Piecewise functions are very helpful in talking about these things, because then I don't have to show you how to do the shortcuts yet. Yes, I'm so devious. All right, for the next two examples, let's determine which domain values the function appears to be. Well, you know what? If we're going to talk about domain values, maybe we should find, as it says here in blue, for fun, let's determine the domain and range, just because we haven't done that in a while. Yes, I know exactly the definition of fun. You are way off. And you know what? This may not fit. We're going to put range down here. So domain. What values are in the domain? Again, is that the X or Y, or the input or the response? That's the input. I don't see arrows, so I don't think it's all of them. So where does our domain begin?
-3.
Just domain. -7? Is -7 included? Do you believe that point is up there? I believe it is, right? So -3 would be included. So how do we notate that again? Bracket all the way to... That's what he said. He said -3. Oh. Okay. Well, he said -3. It is -7. All the way to what? +6, are you sure? What about this point where there's that hole?
It's defined at a different point.
Where's it defined? Oh, down there. Oh, okay. So it is part of the domain. Very good. All right, so there's your domain. Let's do range then.
What's that?
-3, including or no?
Including.
All the way to, because here's -3, right? And there is a value there. All the way to, I think it's 8, right? Because up here's 8. All right, so that was exciting and fun. All right, so now let's find the values on the domain in which it is differentiable. So I'll put maybe, so you can see it, I'll read it up here. So in other words, where can I actually take the derivative? And we're not necessarily going to worry too much about taking the derivative at the endpoints, but you can. You could reel in that derivative at the endpoint. So what do you think? If I was sitting along here on these points, can I take the derivative? Can I find that tangent line? Is it approaching the same slope from both directions is what I'm asking for. And I think it is. Like this point is kind of approaching, that slope. This way it's approaching that slope. So I think it is. So where it's probably easiest to find out where are problems. The cusps, the spikes, any of those are problems. Those discontinuities are really a problem. So I would say from -7 all the way to where is good. We're saying where it is differentiable. All the way to -3, because there is that first kind of spike. And then you can do comma, and then give the next region where it appears to be fine.
-3 to 0.
No, I think we can include them, because you can do a one-sided limit. And we'll include them for now. Yeah, we're going to include it for now because it is a discontinuity. Yeah. And we can clarify that on later problems if we need to. Okay. -3 to where? 0. And 2. And
2, but not including 2.
yeah, that's not a bracket. 2 to, yeah, that's a parenthesis. 2 to what? 6. And I have to decide how I want to teach that.
That just confuses me.
Why is that?
That's pretty much.
-3 is included, 0 is included. So why don't we just do -7 to do?
Ah, very good point. So should we go parentheses? Would you feel better if we went parentheses? Let's do parentheses then. Go ahead. It's fine. Yeah. If you feel better doing parentheses, we'll do it. There. Do we feel better now? Okay. Basically, this is what we're saying. It's good from -7 to 6, except for -3, 0, and 2. Isn't that what we're saying? Right, the same thing, right? How about, that's part A. How about B? Yeah. Well, if you want to keep them not, then we'll leave them not. Yep. We'll keep -7 and 6 not included. Let's do parentheses. We're good. How about continuous but not differentiable? We've kind of already notated where these places are. So where are these places? X equals? Where is it continuous but not differentiable? So where's just one place that is not differentiable? Is it continuous there? So does it meet that requirement? Yep, so x equals -3. Any other places where it is continuous but not differentiable? 0, so up there. Very good. Anything else? Yes. Yes. -7 and 6 are differentiable. Any other ones? Yes. Is it continuous at 2, though? I agree it's not differentiable, but is it continuous? No, because it's not pushing the y value, right? How about C? Neither continuous nor differentiable. Ah, there we go. There's our 2. Any other places that are neither continuous nor differentiable? Yep, I think we're good on that. Okay, here we go. Whoa. Number 2, let's graph it first. So we got negative x squared plus 6. Do we know what that looks like?
Oh, yeah.
It is a what? Parent graph. It's reflected over the x-axis and moved up 6. It has a general shape of a, okay, you could say U, but we have a vocabulary term. Parabola. Okay. Or we could start plugging in values, because it seems like a lot of you like to try that. But we know that's been moved up 6. Yeah, but it's only from -4 to -1, though. Well, that's tricky. Well, let's put in -1 and see where that thing kind of ends then. So if you put in -1, it's really a -1 squared plus 6. Do you agree with that? That's what y will equal in this case, right? And it does actually go all the way there and equal to it, right? So we got -1 squared, which is 1, and then a negative on that makes it a -1, and then plus 6, we're really looking at 5, right? So -1, 5. Right there, right? You with me on that? So now what we should probably do is work our way back out, and let's maybe put in -2. See how it's tricky doing that? You like that? So do -2. -2 squared is +4, but then you make it -4. So it's 2, so it's -2, 2. Now we're going to do, yeah, this is going to be a little harder. Negative. -3. So -3 squared is +9, and then you make it -9, so then it's -3 comma -3, right? And I think we know that it's going to kind of just, whoop, I better stop at -4 though. Yep, no arrow. Yeah, -4 would probably be helpful. I don't think it fits on there though, does it? Is it 10? There you go. Now what? -5x, what's that going to look like? -5, what's that? X, what? -5x, what's that going to look like? A line, very good. What slope? -5. All right, let's put in -1 and see where it goes. -1, you put it in there. +5. So that would really be an open circle there, right, though? But it's already been filled in, right? Because it's not equal to on that one, right there. No equal to on it. And then we'll put in 2 and see what happens, because we have put in 2. But again, that'd be an open circle, because there's no equal to on it. -10. So 2, -10. And open circle, and then we just do our best of connecting them. There we go. And now we'll go to red. And we got x squared minus 4x minus 6. That's a parabola that opens up. You know, we can do some factoring, kind of figure that out. Or we can just do some points and figure out what happens. Like maybe do 2 and see what's happening. So you put 2 in there. What is it? +10 or -10? So it's 2 -10. So it fills it in. Right? And then we put in 3 and 4 and 5, right? We figure out what's going on here. And when we put in 3, we get -9, I think. 3, -9. And then we could do 4, and we get -6. Which is right there. Then we do 5, and we get -1. And then what? It's a hole? Okay. Why is it a hole? Oh, it's not included. Oh, okay. Yeah, it's not included. All right. And of course, for fun, because everybody knows it's a blast. Domain and range. Domain. What do we got?
Just anything or negative infinity to 5 got it.
Not negative infinity. Negative 4 to 5. Now, could we just base it off of this exactly? Like, well, we got to make sure that they, attach and that the points actually get filled in, right? Because what if that point right there hadn't gotten filled in at any point? Then that would not be part of our domain, correct? So you have to be a little careful, okay? And that's why we did not include 5. All right, and range. Is negative 10 included? You are correct. Negative 10 to 5, and are they all included? Yeah, but what about this one over here? Yeah, it's over here and over there, right? Yeah, so it's been included. Very good. So should I bracket the 5 or parentheses it? Okay. So part A is to do what? Say where it is differentiable. Or what some people do is they find out, some of the other ones first. They do B and C first. Would you prefer to do that? Because that's what some people do. They find out where there's problems first. You're good? Okay. So A, we have to find out where is it differentiable. Well, where are there problems? Here's the tricky part. Is negative 1 a problem? Because it is kind of arcing, and then is there a sudden change in that direction right there? Yeah. But you see how I tried to make this one almost look cubic? To see if you would notice if that sudden change was in there, but is there? There actually is. Okay, at negative 1, there is a problem. So we would go at negative 4, and you wanted to do parentheses, right? Okay, negative 4 to negative 1. And then, where's the next problem? Or are we good the rest of the way? Is 2 is a problem then? So you're seeing down here is another one of those sudden changes in direction. Yep, so then it would be negative 1 to 2, and then 2 to 5. So how about B? It says it's continuous but not differentiable. Where are they? Negative 1? And? Is it continuous at 5, though? It's not continuous at 5. How about neither continuous nor differentiable? Remember, they have to be on the domain. Are there any places where it is neither continuous nor differentiable on the domain? Because 5 would be the one we would point out as a problem, correct? But is 5 on the domain? It is not, so you don't worry about it. So, yeah, it is still differentiable there at the end, yeah. 5 would be if it was there. If 5 was there, it would be differentiable at that point, yeah. Right, because 5 isn't there. Oh, that would change. Well, you mean this one would change, or which one? It is continuous, though, at that point. Yeah, it'd be fine. Yep. C would still be empty set, yeah. Yes? Okay, the question was, what if it was negative 5x squared in the middle instead of negative 5x? This would change drastically because I don't think the graph would look anything like what we have now. because instead of a line connecting those, the green and the red, we'd have a parabola, and then that probably would not connect them at all. Yeah, it would be a drastically different setup. So it would affect it a lot. In other words. Sure. Another question.
What would the differentiable be?
Okay, I believe the question that's coming up is, what if I was able, and you can, I was able to find the function that brought the slopes in here gradually and sent them back out. Okay, can you do that? Yes, you can. It's somewhat difficult, but you can do it. Okay, would that affect our answers for A, B, and C? If I could put a piecewise together, that would make this work out. Yeah, I would change that drastically if I could put that function in there that doesn't make that drastic change in those slopes. Okay, then what would really change? Well, would basically -1 still be in this spot here? No. And then would I really have to have this here then? No, I could have just gone -4 all the way to 2 if I was able to put those functions together. Same thing down here, you could do the same thing. They are, yes.
I'm waiting till we get the assignment.